Yeah, good day, guys. Today we are looking at DC machines. We want to classify DC machines based on their excitation method. Now, a DC machine is an electromagnetic um, equipment that can convert electrical energy into mechanical energy and vice versa. It can equally convert from mechanical to electrical and also from electrical to mechanical. So when a DC machine converts from electrical to mechanical, we refer to it as the DC motor. The terminology here, DC, is that's direct current, meaning that our voltage to time wave form is in this order, in a straight line order. Doesn't have a negative part like alternating and like an AC motor that has this positive and negative part. So this is our DC with your oscilloscope. Why making reading from this? This is how that's if this is a generator. I guess I didn't say what the generator is. A DC machine can either be a generator or alternator, no one you choose to call it, or motor. Now the generator converts electrical and mechanical shock into electrical. While motor on the other hand converts electrical into mechanical. So in case if this is just the basic knowledge of a DC motor. When you are asked about the DC motor, they might either be talking about the generator or the motor, and theoretically they are almost the same thing. In fact, based on even construction step, they're almost the same. A DC motor can either serve as a generator or as a motor, depending on what the output and the input is. If the input is mechanical and output is electrical, then you're going to be you're using that DC motor machine as a generator. But if the input is electrical and the output is mechanical, you are using that DC machine as a motor. Now, like I said earlier, your wave form, that's if you're using as a generator and you're going to create an electrical signal. If you're to measure with an oscilloscope, this is how your waveform will look like. As you can see, it's not purely DC. It has a little bit of rectification to do. I think if it comes to rectifiers, I think the one I normally should have this is a half wave rectifier. I don't want to go into that's a full wave rectifier. I don't want to go into that. I want to go into that now. So our focus is DC machine classification based on their excitation method. Now, whether, like I said earlier, a machine can serve as generator and motor. So, whether generator or motor, they can still be also classified based on their excitation method. Sorry, they can be classified based on their excitation method. So, that is our focus today. That's our focus today. Now, you have your DC, your DC machine. Now, this DC machine can be further classified based on their excitation method into, you have your self excited motor or machine, and you have your separately excited machine. Now, the like you see here, I wrote self-excited machine. Here okay, let me start by saying this. A DC machine has two major components. We have your sorry, you have your field magnet. In alternating, that's AC machines, we do refer to this as the stator, but here we call it the field magnet. This is the first major part of the DC machine. Now, the next important part that we need to consider is the armature. The armature is more like the rotor. It's more like the rotor. You when you are to look at the parts of a DC machine, I think you if I'm going to make a cross-sectional image of the inside, you have your your pull core, and it is holding the pull coil, and this pull core is actually attached to the yoke, or to what you call the body of the DC motor. Why this guy is your pull core, and this guy is your pull coil, which is typically band of wire that's being wrapped. So when it's being energized, that's when current pass through it serves as a magnet, typical electromagnetism. That's just what is happening. Now, lately labeling not coming way of drawing. Let me explain this. Now, then due to inductance, that is how your motor is actually operated. It's due to inductive capacity. That is how this motor actually do this conductive ability. That's how the motor actually conduct runs. So at the center you have your armature, and this armature actually is it has both a core, which is the one in the center. It is actually the no, so it's not how it looks like. It has teeth. Normally has teeth, which is where your armature coil or conductors actually fixed into. So it has teeth like this and some holes or perforation for allowing airflow. Then it also has the hole for putting your shaft. Your shaft is the pin that protrudes out of the DC machine or the metal or whatever you want to call it that protrudes out of the DC machine is actually what you call it, the shaft. And that shaft kind of is actually paired to this armature through a kind of keyed opening here. So the shaft will have something that will fit into this hole so that it won't be able to easily detach or stuff like that. So it won't easily go out. So in basically, this drawing is not complete. I just made a rough sketch and quick explanation. Then inside here, you then have your armature winding or your armature coil or conductor inside here. But this particular metal with the hole, this is actually a hole where you insert your shaft. They are all part of your armature core. That does the mechanical part. Your yoke, your pole core, and your armature core have no this thing, have no electrical usage. They're just supportive and kind of backbone, holding something together for the other electrical parts. So this part they don't have any, they don't have any impact electrically to the motor's operation. They just get to kind of hold the main things like your pole core and your armature wind or conductor that's actually inside this pole and even your shaft. So all these are not actually, they're just kind of a backbone skeleton for the main things. These three items I made mention of here. So like I said earlier, the two important parts of a DC motor are the field magnet and your armature. So this region that's from the yoke to the pole core and pole winding and coil, we refer to them as the field magnet. I just say FM. That's not only the symbol or how it's noted, but I just want to abbreviate it here. It's actually called the field magnet. Then from this region down to the shaft and armature winding and coil, the rest of them we just refer to them as the armature. The thing we also do call it the rotor AC uh, machine. But let's not deviate a bit. Let's not deviate too far. The main focus is that we have major parts, two major parts, which is this and this. Now, for your machine to be called self-excited machine, what it means is that it is actually the one that is supplying um, current to the generator or the machine. Yeah, the generator or the machine is actually the one supplying current to this field magnet. This Mr. Man here, the first one, for it to be self-excited. because your self-excited, like the word says, means that it is the one exciting itself. So it is not getting its excitation or its current from an external source. Unlike your separately excited machine, this one has a separate source, something that excites the field magnet, like I drew here. That will pull side, your your pull winding, your pull coil, your pull coil. So it is actually in the self-excited, the machine actually is the one exciting this guy. But in your separately excited machine, this guy is excited by an external DC source. So let me make a sketch or electrical diagram of what I mean. So your yourself looks like this. It actually under yourself, I won't draw self now because it has other subgroups. So it doesn't have a particular form. It has like three other subgroups under it. And under that ones, other ones too. But we'll come to that. But for this our separately excited machine, you have your DC source connected to your resistor, variable resistor, then to the armature or the armature, to the field magnets, to the field magnet. This is your DC source, and this is your resistor, or variable resistor, whatever you choose to call it. This is your field magnet. You can also say FM in short, but that's not the kind of, I don't think it has an abbreviation or stuff like that. The FM I know is frequency modulation. Let's not go into that. So as I was saying, now this guy, this field magnet is energized. It receives its own current from a separate DC source. Now you then have your generator, which is now connected to the terminal, another external holder, another external electrical component. So this this guy is energized by another DC source, an external DC source, and it's separate from your generator, from your machine. It's separate from it. So the field magnet, which is kind of the static part, doesn't actually move. It's always static. I think the one that normally do move is the armature, the rotor, the shaft, whatever one, the one that are moving. But this guy remains static. So this is separate from the generator, the armature, the frequency. The field magnet is separate from the generator. That's why we call it a separate excited machine. Now, coming over to our our self-excited machine.
The field magnet is excited by the generator.
So under it, you have other change. Under it, you have three other subgroups. The first one is your shunt short one machine, and the second one is your serious one machine, one machine, and the last one on the list is your compound one machine. Self-excited machine is subdivided into shunt one, series one, and compound one. Now, the short one is um which is under the self-excited machine. That is, the generator is the one that is supplying current to the field magnet. Now, for the short one, we have the electrical diagram to look like this, where you have your field magnet connected in parallel with your armature coil. So with this, now your armature, in this case we are using a generator analogy. Your armature rotates, want to generate electricity. So your armature, which is the rotor, the stuff connected to the shaft, the mechanical part, or the part connected to the shaft, when it rotates, it produces current, which we call the armature current. And this also, like, since it's coming to this node, it is going to split into two. One moving over to this place, which is your load current, and one your short current going to the field magnets, to your field magnets. So that's for the shunt one. It is connected in parallel to, and the field magnet is connected in parallel to the armature. And for the series one, you have your motor, your armature, so connected in series with your field magnet. Now, since the armature and the field magnet are connected in series, you only have one current, because it's a series connection. You only have one current. But on the other side, which is at the when you're looking at voltage point of view, at this point, this guy has the same voltage, the same thing with the armature. Each of them have equal voltage since they are connected in parallel. So if this was to be a motor and it was to supply, instead of receive, it was to supply we are to supply electrical current into this circuit, or to supply current into this circuit. Though at this point your current might split into two, but your voltage still remains the same. Unlike here, that you have your field magnet connected in series with the generator. For this purpose, your voltage won't be the same. At each of these components, you will have a voltage drop making your voltage, the voltage applied to both the field magnet and the generator, sorry, the armature, not to be equal. So that's just their one of the advantage of um, the shunt over the series. Yeah, and it's also worth noting that series one actually are also used in boosters because of their connection. It is quite useful in boosters. Now the our friend here on the other hand, which is compound one, is kind of a combination of the other two. Compound one is combination of the short one and the serious one. Now let me clean this and make room for also. Now the compound one is also subdivided into two. So it can also be classified into other two subgroups due to the fact that one, our shunt wand is stronger than our series wand in the compound and wand um, connection, and it has two subgroups, like I said, namely the short shunt and your long shunt. The short shunt and the long shunt. Now, if you notice, they didn't use series, but we didn't use series, but shunts. The reason is because of our shunt is stronger. The shunt connection is stronger compared to the series. Like we said earlier, the series doesn't have equal voltage, but has equal um, current. So the shunt is stronger than the series. Now we have two, which is short and the long. There's a slight difference. Like we said earlier, there is one compound one is the combination of the short and the series. Now coming over here, let's make a column for this. Coming over here, let's for the short shunt. Now we have our armature. We have our armature connected in series with a field magnet. Now we won't we'll be tapping from the tapping after the armature and before the series connected and the series connected field magnet. Now I'm connecting to another field magnet. So as you can see, this is typically this region over here is typically your shunt zone, while this other region is your serious one. So as you can see, it's just a combination of the two. Just a combination of the two. Now the only slight difference between this and the long is that coming to the long, coming to the long, coming over to the long. What? Now our our shunt field magnet is connected after the series connected field magnet. So this we call this the long shunt, and at this terminal you have your load currents. At this point you have your armature current, and at this point you have your shunt currents. So these are the slight difference for the long. So this is just the slight difference between the two. They are the reason why they are both under the compound wand, and the slight difference is just that for the short you have your tapping after your armature, while for the long you have your tapping after the series connected field magnet. That's the difference, but they are both the combination of your shunt and your series one. Now, for the two of them, both your short and long, your short and your long shunt, they both have subgroups too, called cumulative and differential compound machines. Now, when your serious wand is aiding your short wand, we say that the compound wand is what? Cumulative. Let me write this over here. So when your serious wand is aiding your short wand, hmm? Serious aid short. When your series is aiding your short wand, we say it is what? Cumulative. But while when your series is opposing your shunt wand, then you say that it is differential. You say it is what? Differential. So that's just the classification of DC machines based on the excited method. I hope this was helpful. Please subscribe and click the notification bell for more content. Thank you.